right? And their relation to automata. And let's see. So let's first start with a review of notation. Right? I don't know if you can see this, or should I enlarge this thing? I can also enlarge it like this way. And I can also use my pen, hopefully. But if I use my pen, I cannot. So this is the downside. Okay, so if I use my pen, somehow I cannot zoom in. But anyways, let's try to proceed this way. So what is an alphabet, right? So alphabet is just any finite set. So should we start with some kind of an introduction? Okay, let me just say the definition of a language, and then I will say why is it so important. But let's start with an alphabet. So alphabet is any finite set. So the reason for naming a finite set an alphabet is because you can think of it as an alphabet for our intents and purposes. So for example, you can think of an, I don't know, Latin alphabet. So the Latin alphabet will be a set like A, B, C, D, E, F, I don't know, Z. I don't know if Z was included in Latin alphabet or not. And also maybe capital letters. Let's also include capital letters A, B, C, and so on. Okay, so Latin alphabet will consist, I don't know how many ever letters Latin alphabet had, plus the capital letter. So that would be a finite set. And so we call any finite set. So maybe let's take another example as well. Let's take example 0, 1. So this Boolean set you're aware of, this is just contains two elements, 0 and 1. This would also be a finite set, of course. This can also be taken as an alphabet. Georgian alphabet can also be taken as a set. So this contains, we do not have capital letters, and so like this, whatever. So the cardinality I will denote by a hashtag. So for example, hashtag B would be 2, right? And hashtag of Georgian alphabet will be what? 33 letters we have, right? Now what is a string or a word? So a word with letters in A. So I fix my alphabet. So let's say I fix my Latin alphabet. So I fix my Latin alphabet and I say what is a word there. So word also means that your alphabet is fixed. A word will be any combination of symbols from your alphabet. So for example, A, B, 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 C will be a word in a Latin alphabet. Also, the actual what humans mean by word, these things will also be words. For example, D-O-G will be a word, but it's also a dog, right? So any combination of those letters will constitute a word. For example, if I fix B, then any string of zeros and ones, any finite string of zeros and ones. So you have to have start and a finish will be a word. Okay, so it's not quite the same as so in Georgian, like for example, this will be a word, and this will be a word. And this would also be a word, but anything gibberish will also be a word. So any combination of strings is a word. So this is a word, or sometimes just call it a string, because just taking an analogy from here, then it's a string. Then length will be just denoted as a modulus. So modulus of string B is L. That means it has L letters in it. Okay. Now let me define a concatenation of words. So if I have two words, let's concentrate on strings. So let's say I have this word. So my alphabet is just 0, 1. And I have this word. Then I can concatenate them. This just means I just write them like this. Right? So I just put them together. So this is concatenation. So I just write them. If B is a word and C is a word, BC is just, I start with B and continue with C. I think you have seen it somewhere. And then by AI, for example, I don't know if I can erase this now. Erase all ink on a slide. Very good. So what is AI? So let's fix our alphabet. Let's fix our alphabet to be 0, 1. since we're doing computer science. So we're looking at all possible strings. The words are strings. And what would be B, let's say 2? B2, under this notation here, means all words that have length 2. So this will include what? 0, 0, 0, 1, 1, 1, and 1, 0. So B2 will be something like this. Okay, B3 will be all strings of length 3. So if I write it this way, what would be the size of B3? Or maybe written this way. How many strings will be included in B3? 8, yeah, because it's 8, basically. Because it's 0, 0, 0, 0, 0, 1, 0, 1, 0, and so on. So there's 2 to the 3 possibilities of writing strings this way, so there will be 8 strings in here, right? And then by A plus, for an alphabet A, I mean the union of all such things. So for example, B plus would be union, I goes from 1 to infinity, of all BI's. So it will include all possible strings that you can create of some finite size that you can create from B. So this will include, for example, 0, 1. This will include all the things here. So 0, 0, 0, 0, 1, 1, 1, 1, 0. All the things in here, which has 0, 0, 0, and so on. So it just contains all possible strings of all possible length, created from your alphabet A. Okay? So let's look at another case. If my alphabet was Georgian alphabet, as I said, then this thing would be all possible words in Georgian that are not empty. So basically like A, B, then B, 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 G, or whatever. Also the words, actual words, like this will be here, and so on. So all possible words. So it's like you're looking at a dictionary that has all possible combinations of Georgian letters. Right? So this thing is huge. Okay, now we also add one more extra word to this. We call it an empty word. Empty word is just no letters. So it's hard to imagine because there is no letters, but we can denote it by epsilon. So epsilon denotes this. So there is nothing written here, basically. So it's an empty word, and it is characterized by the property that if you take any string and concatenate it with epsilon, it stays the same on either side. So you have a string, let's say again my alphabet is 0, 1, and if you have this string here and I concatenate it with epsilon, epsilon basically means there's nothing there, it just stays the same. And I can do it on the other side as well, and it still stays the same. So this is what an empty word is. It's just a formal definition. There's nothing deep to it. And then by A star, this is a very, very important definition for us. We will use it all the time. It's again A plus, so this thing, all possible strings from A, plus the empty word. So in here, if I add one more guy here, namely epsilon, then I will get A star of 2. So A plus and A star only differ by one thing. A star has an empty word added to it. That's it. So A star is basically, so my mouse has disappeared. So A star is basically A plus and an epsilon by definition. So it's the same as taking a union but starting from 0. Here you started from 1, you see. So if you start from 0, A to the power 0, you might call it epsilon. So just one set that contains epsilon, and then it's the same. You get the same kind of definition applies. Okay, now we come to the main definition of a language. A language is a subset of A star. So this is a radically abstract definition. Why does it make sense? So let's go back here. And let's again think from the analogy. This analogy is not good, by the way, but this analogy is where the naming comes from. So let's just use it for now. So let's take actual Georgian dictionary. Let's say I have a Georgian dictionary laying here on my desk, and I look at all possible words. All of them appear, so every word in Georgian language, let's call it every word in Georgian language, will appear in A star, right? Because A star contains all possible strings, so it also contains legit Georgian words. But there are more things in A star than just legit words. For example, this guy here does not appear in a dictionary, right? Only some of the words appear. So the Georgian language, so let's call it language Georgian, will be a subset of all possible strings over Georgian alphabet. So nothing special. So a language is just you fix a certain subset in all possible combinations. For let's move on and look at, let's say, if my alphabet is 0, 1, and I look at B star, which is all possible finite strings of zeros and ones, then a language will be any subset of this thing will be a language, right? For example, language can be a finite thing. For example, 0, 0, 0, 1 will be a language. It just contains two strings, 0, 0, 0, 1. But infinite things also will be languages. For example, a language can be something like this. 0, I, 1, I. Let's say when I is a natural number. This means, what is this? This is all possible strings that have as many zeros in the beginning, as many continued by the same amount of ones. For example, this contains, so the natural numbers, let's say, so it starts with 0, 1, 0, 0, 1, 1, 0, 0, 0, 1, 1, 1, and so on. Why is my mouse not visible? Here. Okay. So you mean here, right? Exactly. So I defined a to the power 0 as being something like this. And this is why A star is exactly A plus. So let me write this down here. So A star, by definition, was a union. Let's start from 1 to infinity AI, and I take a union with empty set. This is A plus. And this I can call A to the power 0. And then if I do this, this is the same as going from 0 to infinity of AI then. So it's just a convention. I can call this A0 just a set that contains an empty word. And then I can take the union from 0 and then A star will be defined this way. And this is what is happening here. No. So let me erase all the ink. Okay, yeah. And now the language basically is just a subset of A star, as I said. And this is radically abstract definition. And let me, before I proceed, why this thing can be important, let me just give you a small introduction. Because anything, basically, any problem we face, specifically algorithmic problems, but other ones as well, can be encoded as a language. Let's first look at this, what they call decision problems. Let's say you want to find out, you're given a number, this is a usual example. Let's say you're given a number n, and you're told, is n a prime? So this is your question. So you're given a number, and you're supposed to come up with an algorithm or whatever. So you're supposed to answer a question, is n a prime number? Suppose you have a language, let's say. So let's say let's write it this way. So let's say your alphabet is all natural. Just let's make it simple. I will show you exactly how this thing is done. But let's say this is your alphabet, right? Then A star contains all natural numbers and also non-natural numbers. So it contains things like this as well. but it also contains all natural numbers. Right? So all possible strings you can make from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 contain all natural numbers. It also contains things like 0, 0, 0, 1, 9, which is not a natural number, but it also contains natural numbers. And let's say I have a language LP, which is a subset of my A star, like this, which only contains prime numbers. Right? So LP contains, what are the prime numbers? 2, 3, 5, 7, 11, and so on. So it contains only the prime numbers. So it's a language on A star when I only pick out those strings that represent prime numbers. Then your question here, is n a prime number? Now translates into a question, does n belong to LP? So if I devise an algorithm that tells me for this language, it tells me whether when I give you a string for a computer, it has no meaning, right? It only has, so to say, syntax. So the prime number has no meaning. It's just a string. String, let's say 27 is not a prime, whatever. 11 is a prime. So it's string 1, 1. So it has to check whether this string belongs to LP. So if there's an algorithm that checks this somehow, and it returns yes, it answers the question whether n is prime. And if it returns no, it's a decision problem. So yes, no problem. The decision problem is a shorthand for yes, no problem. So if every yes, no problem can be translated into a problem which asks, does something belong to a language? Let's look at another example. Is this triangle a right triangle? Let's say this question. Then you might create a language that contains so you have your Cartesian coordinates, let's say, and you create all possible triples that constitute a triangle, and you create a language that only contains those triples, so those things like x1, y1, x2, y2, x3, y3, only those triples that constitute a right triangle, and then your question translates to, does this specific triple belong to this language? But what should the alphabet here be? The alphabet should be all possible real numbers and also parentheses and small ones and stuff. But you can do this. So it's doable. But I'm trying to say, we will discuss this much in greater extent. But what I'm trying to say is that any problem can be translated into a language kind of problem. This is why these things are important. And we are going to do this. This doesn't help at all to solve the problem. What it helps is to formalize it. So it's the first step. So you completely formally describe something, and then we will describe what the problem means and how to solve it. Doesn't say anything how to solve the problems. What I'm claiming now is that every problem, well, decision problem at least, that has yes-no question, can be translated in terms of language. This is all I said, but it doesn't help for now. It's just a framework. Okay, so let's erase all ink again. So let's do some more. So what is a concatenation of languages now? So let's say I have two languages, so two subsets of A star, L1 and L2. L1 concatenated with L2 is I take all possible concatenations of BC like this. Words, well, the first word is from L1 and the second word is from L2. Let's do an example on this. Let's grab this. So let's go to a more civilized place. So let's take our alphabet is again B. So you always have to fix the alphabet. So in our case, B is 0, 1. And let's just review again. B star is all possible strings. So it includes the empty one. It includes 0, 1. These are length 1 strings. Then maybe length 2 strings. then maybe length 3 strings, and so on, and all of them basically. So B star is an infinite set. However, every string inside is finite. Right? This is B star. So let's take two finite nice languages. Let's say L1. It should be a subset of this guy. So let's take, I don't know, 0, 0, 0, 1, 1. That's it. And let's take L2 equal to, I don't know, something else. 1, 1, 0, 1, 1. Then what is L1 concatenated with L2? It's a new language where the first part of the word is from L1 and the second one is from L2. So it will include things like 0, 1, because I took 0 from here, 1 from here. It will also include 0, 1, 0. So I took 0 from here and 1, 0 from here. It will include 0, 1, 1. Because 0 from here, 1, 1 from here. It will also include things like 1, 1, 1, 1, because 1, 1 belongs to both of them, so I took 1, 1 from here, 1, 1 from here. What else is there? So, for example, 0, 0, 1 is in there, because I took 0, 0 from L1, and so on. But it will be finite. There's only finite many ways I can do this. Right? There 3 ways here, 3 ways here, so you think about how many ways are there to do this, but you get the concatenation like this, right? Pay attention that this is not the same that if I do this. Can you give me an example of a string that is here but not here? Oh yeah, sorry. Exactly, because 1, 0 is here because nothing will start with 1, 0 from L1. So 1, 0 is here because 1 is in L2 and 0 is in L1. So you can concatenate this way. I took 1 from L2, 0 from L1. However, here I cannot do this. Nothing starts with 1, 0. Okay, so this is a concatenation of languages. So I can concatenate languages like this. Let's just look at it this way. And let's define a complement and a star again. So let's come here. What is a complement of a language? Let's say L1 complement. This is everything that is not in L1. That means, so I take B star and subtract L1. This will be an infinite language, but it will not contain, let's say, 0. It will not contain 0, 0, and it will not contain 1, 1. Everything else will be in here. So everything other than things that are in, 0, yeah, correct. So other than things that are in L1. This is a complement of the language. And now we define, if we have L, what is L star? L star is concatenating L with itself as many times as I like. So basically, this means, so let's look at you never looked at the definition. My mouse is not working. So what is L star here? L star is basically you take any number of words from 1 to S, and each word is in L. So you take strings from L and concatenate with itself. So basically, for example, this will include things like 0, 0, 0, 0, 0, 0, 0. It will, because I took 0, let's take, this is L1. So I took 0 from L1 and I concatenated with itself as many times as I like. It will also include things like 0, 0, 1, 1, 0. Why? Because it's 0, 0, then I took 1, 1, and I concatenated with 0. But it will never include 1, for example. So you're taking your language and taking all the strings it has and you're just putting them together in all possible ways that you get finite strings. This is L star. Let's say let's take an example. Let's look again. Let's say B is my language, my alphabet, sorry. And let's say my language just only contains 0. What is L star? Exactly. So it will have 0, 0, 0, 0, 0, 0, 1, 2, 3, 4, and so on. Jogor? So the fact that this is your language I took, so let's give it a number. Let's say L1 is 0, then I took this specific language, and L1 star is a completely different language than L1. Oh. ეს არის ერთხელ გაქაღებული, ეგ შეიძლება, კი. But the fact that can we do it 0 times, let's not do it 0 times. Let's say that this guy, maybe we will need this later. Huh? So the question here was, is this guy included here? This is a matter of convention. Let's not include it. Let's not include it for now. We will add this later. If L does not include epsilon itself, then L star will not include epsilon either. So it might be that L includes epsilon like this, and then you will get this, yes. But if it's not there, let's not include it. So, but this is a matter of definition that we might change it at some point.
Can epsilon be concatenated with any other string?
Yes, if you concatenate epsilon with any other string, it just stays the same.
So if we had epsilon there, it wouldn't make a difference?
Exactly. In building L star, the only difference it would make, it would just include epsilon also. That will be the only difference, yeah. But this is just a matter of definition. This is not some deep fact. We can then change it later. Okay, so now I have this. Oh, okay, let's take a break now. Okay, so we continue with the lecture. So this was basically notation. This is all we did. So we just defined some terms and just gave some notation for some things. We have not done anything special. Now we move on to actually exploring these languages. One thing that you might not have noticed is that when I took this A star, which is an infinite set, so I fixed my alphabet, I took all possible strings on that alphabet, and I fixed some subset. This is already we were very much in deep waters. This is what I mean. There are many very complicated languages here. So what we're trying to do now is to isolate some simple languages. So I will isolate the class of languages. We'll call them regular languages, and I will specify which languages are regular. And these are, so what basically I'm doing, because of my introduction, is I'm classifying problems. As I said, all languages can be translated into some problems, and all problems, specifically some, decision problems at least, not all problems, but decision problems can be translated to languages. So now what I'm trying to do is I'm trying to classify which problems are somehow easy to solve, somehow algorithmically, and which problems will be hard to solve. And the first class of problems or class of languages I'm going to tackle are called regular languages. So what is a regular language? So we start with a definition of a regular set over an alphabet A. So everything I do will always be over an alphabet. So let's for our example, let's fix our alphabet is, 0, 1 again. So what is a regular set over alphabet A? It is a set that contains empty word is regular. This is my first declaration. So if you have a set that only contains an empty word, this is a regular over alphabet, let's say 0, 1. Okay. Now, my second declaration here is that every letter of my alphabet, if I can look at every letter and consider a set, that will be regular. So let's discuss in our example. By 1, for example, this thing will be regular. By 2, these things will be regular. This is what 2 says. So if you fix an alphabet, every letter considered as a set is a regular set. Okay? And number 3. What number 3 says that if you have 2 regular sets, L1 and L2, then their concatenation, union, and the star are all regular. For example, here, I know 0 is regular, 1 is regular, so their concatenation will be regular. What is their concatenation? It's 0, 1. Okay. Now I know 0, 1 is regular. I know 0 is regular. So then their concatenation, which will be 0, 0, 1, this is also regular. Okay, now I have 1, 2, 3, 4, 5 regular sets. So I can take any union of the 2. For example, if I take the union of 0, 1, 0, 0, 1, this will be regular. I just took the union here. Now I have 3 regular sets. Again, I can take a union. For example, I can get 0, 1, 0, 0, 1, empty. And again, let's take a union again and 0. This guy is regular. Now I can take concatenation of these 2 things, for example, and I will get 0, 1, 0, 1, 0, 1, 0, 0, 1, 0, 0, 1, 0, 1, and so on and so forth. So you see that I can build the things here, and again I can also take clean star. For example, if this is the only place I can become infinite somehow. So if I have 0 is regular, what is the star of 0 again? I don't know if we answered this question. Oh yeah, we did. So it's something like 0, 0, 0, 0, 0, 0, and so on, which is basically can be written in shorthand this way. 0 to the power n, where n is a natural number. So I'm defining what regular means. What I'm saying is empty set is regular. I'm saying that every letter considered as a set is regular. And now I'm saying if 2 things are regular, their concatenation, their union, and the star is regular. So these things will be all regular. And number 4 says that that's it. If you cannot build it this way, it's not regular. So now if I ask you a question, which is this set regular? What you can only answer is, can you build it from these 3 things? Can you build it from single letters, empty set, concatenations, unions, and stars? If you can do this, then it is regular. Amashirat shedis, the things that are included here, are called regular. Oh, that's a very good question. If I give you a language, for example, I give you the language that we had before. Let's say take this language. It includes 0, 1, 0, 0, 1, 1, and so on. So it's basically this, 0i, 1i, for I being a natural number. This is a language that only includes strings with similar amounts of zeros as 1. Now I'm asking a question, is this regular? So let's actually try it. Let's do the recording and I will show you one more example. Maybe this is where the confusion is coming from. So let's go here and so what did we have? So the regular thing, the first one was that we had epsilon. The second requirement was that for any a in my I fixed my alphabet. Let's fix our alphabet. So my a is just 0, 1. Just simplicity. Right? So for any in B, so basically these 2 things. I have here this guy and this guy is regular because I only have 2 letters. And 3, I had that if I already have regular languages, then I can take their union, I can take the star of any one of them, and I can take their concatenation. Good. So let's look at example. Let's look at 0, 1. So I know 0 is regular, 1 is regular. What do you want to do? If I take their union, this is regular. I can take a star now. If I take 0, 1 star, this is what? This is everything. This is all possible strings of zeros and ones, like 0, 1, 0, 0, 1, 1, 1, 0, 1, and so on. Then, even though we did not allow taking star to include epsilon, epsilon is here, so I can take 0, 1, star, and union epsilon, and then I will get everything completely. So epsilon 0, 1, 0, 0, 0, 1. So everything is, so if I take everything, this is regular. However, that is the point. I know that this language, 0 to the power I, 1 to the power I, so this language I belongs to n. So this is just a shorthand of writing this set. 0, 1, 0, 0, 1, 1, and so on. I know that this is a subset of B star, right? So this is a subset of this thing. So it is a subset of a regular language. But it's not clear that this is regular. The whole point is that when you're building your regular language here, you do not have to overbuild somehow. You should exactly get this thing. So let's say it in English. So what is the gist here? The gist is that this is somehow all the information. So all possible strings are there. Specifying all the information is very easy. So maybe I should talk about specification, what it means. But let's talk about the specification, and then I will come back to this. So let's continue. So these are the regular sets, and by the way, number 4 is also very important here. Number 4 says that you do this is regular, these are regular, and then nothing else is regular. So if your language cannot be built from these building blocks, then it is not regular. So what you really do, so now let me, do you guys know the difference between, I don't know if you met it somewhere, between syntax and semantics? Good, somebody is saying yes. So semantics is like a content of your whatever you're talking about, where syntax is only just the string representation without the content. So what I mean here, now I want to specify the syntax that describes regular sets. What I mean, let me show you this. So let's say you're building a regular set, and we had the example when we had the alphabet was 0, 1, and we built that this guy, let's say 0, 0, 0, 1, 1, 1, or whatever. We proved that this is regular. How did we prove this? We built it from the building blocks. So we knew that 0 was regular, we knew 1 was regular, then we concatenated something, we concatenated 0 with 0, we got 0, 0, then we took a union with whatever, then we concatenated 0, 0 with 1, blah, blah, and then we built this set. So we kind of write the code how to build this, and then this becomes regular. What regular expression does, it's a syntax on how to specify regular sets. Let me explain. So what is a regular expression? This is purely syntactical thing. This has no meaning anymore. For example, when I was talking here about the set that contains empty word, this was a set that contains empty word. I was giving it a meaning to you. But if you're inputting this in a computer somehow, this has no meaning at all. It's not a set that contains empty string. It's just some symbol. So regular expression is just a manipulation of symbols that I will need to describe a regular set. So let me give you a definition, and then you'll see. I will say that epsilon is a regular expression. This is just a symbol. So symbol epsilon I'm allowed to write down. Then number 2 says that if there is a letter in my alphabet, I can write down this letter. So this is my regular expression. Then this one says that if I have 2 regular expressions, C and D, I can write down C circle D. This does not mean concatenation anymore. This is just a string. C circle D, C cup D. This doesn't mean union anymore. It's just a string. It's just a syntactic expression, and C star. And these are all again. So for example, if so in my case, when B is 0, 1 again, I know this is a regular expression and this is a regular expression. And now I have to write parentheses. I'm not allowed to write parentheses, but let's just write parentheses for the sake of it. Otherwise, I have to think which one is preferred first, like we do in high school. But let's just write parentheses. Let's say we're allowed. Then this is again a regular expression. And maybe then this is a regular expression. I'm not allowed to write parentheses as it's written here. However, I write them because otherwise I can come up with the order of the operations. Somehow I can write this down instead. But I might say that I always think that they're parentheses from the right or something like that. Or I always say that I always perform star first and then the union. I can come up with the definitions like this. The same exact way, if you have expression like this, what is this? So if you do addition first, it's 4 times 5, it's 20. But if you do multiplication first, as we were taught in school, it's 16. So somehow we came up with the rule that we do multiplication first, and then this has a unique meaning. I can do the same exact thing here as well. But to get rid of this ambiguity, I can come up with the parentheses and write something like this, and then it's clear that I do this first. So the same thing I did here. So this is just a string. It means nothing. It has an alphabet letter, this symbol here, this symbol, and this symbol. This is a regular expression. Not everything is a regular expression. Only things that contain epsilon, letters, and these symbols here are regular expressions. Okay? So this is a string that is supposed to describe a regular set. So in regular set, I was saying things like union. But what is union, right? Union is it has a semantic component to it. You know what the union is somehow. But in string, this is just nothing. This is just a symbol, C-U-D. So this is araperiara. This is just a symbol. This is just a symbol. Yes, we write it this way. We write it exactly as it's written here. Okay? And now what I'm saying is, how do I interpret? Now I want to kind of specify, how do I interpret? How do I give this syntax some semantics? So how do I interpret this string here? So I'm interpreting this string by what I say, a language generated by an expression E. So let's say our expression is what? 1 cup 0. So this is just a string, right? 1 cup 0. How do I interpret this? L of this. So now this is a language generated by this string. How do I interpret this? If your string is empty, I interpret this as a language generated by an empty string. If your string is just one letter, this is just that letter as a set. But if your string is something cup something, in this case, this one, then let's use this here. Then this is the same as L1 cup L0. But on this side, there's a great difference between this cup and this cup here. It's not written, but on the left side, it's just a string or just a fake symbol U, but on the right side, it's the real union. Syntax world, stringevia, the syntax are just strings with no meaning, and semantics is the meaning we give to strings. And this is what this explains. Then this here, by the first rule, this is just 1 union with 0 by the first rule here. And this is now just a real union, so it's 0, 1. So this string here with no meaning generates a language 0, 1. So regular expressions are just how you code your computer somehow to talk about regular languages without computer knowing what regular languages really are. So this is the idea here. We're being very careful here, and we're building from zero. So just to reiterate, so if you have C circle D, this here, just to reiterate again, this here is purely syntax. So this has no meaning. It's just a string C circle D. This here, on the other hand, is concatenation. So it actually would be good if this is a different symbol, but it's the same symbol. This is a string symbol U, whereas this is just a real union. Again, this is just a star, which means nothing, but this is an actual star. And then I will say that the language is regular if there exists an expression that describes it. So basically, when I was asking you, for example, I was asking that, how will you build this guy? Right? I asked you this, how will you... What I was asking, tell me the regular expression that specifies this language. You were supposed to tell me, take the union, then intersection, then the star, blah, blah, blah. So you have to take a regular expression, which is finite. It has to be finite somehow. That when you think of it semantically in your head, it generates a regular language. And think of it semantically is actually defined here, even though it's not completely defined, because on the right side, what does it mean to take union, but whatever. So, for example, if I let's take a regular expression. What does this regular expression, which language does this regular expression generate? There was this erase everything or something, yeah. So let's take a regular expression like this. What language does this generate? Yeah, so what you're supposed to, L of this is what language does this. Use this. This is the same as L of 0, but now the cleany star, the real one, L of 0 by 1 is just 0, and then you're taking star of it, and this is just all possible zeros. 0, 0, 0, 0, 0, 0. So this is infinite. Even though the regular expression was as small as possible, so it's just one thing, it described this language. For example, this regular expression, and then a star like this, even though I'm not about to write parentheses, but whatever, this is everything. This generates all possible strings, basically. So it will generate all possible strings. Even though the description, the expression, the regular expression is very short. It has 2 symbols. 1, 2, 3, 4 symbols. 1, union, this guy, and this guy. 우사스로 description이 вообще infinite description doesn't even make sense in some sense, because how can you read the description which is infinite? But anyway, so any description in our computer, any algorithm has to be a finite string. This is what we're aiming for. Also, the regular expression is a finite string. Can you have an algorithm which is infinite length? Somehow makes no sense, right? That's the idea here. Let me give you some examples of regular languages. So let's actually copy this. Let's copy this and let's actually discuss it in a different environment. Let's discuss this here. Let's discuss this here. Yeah. So this is a better environment to discuss it. So first I'm claiming that all sets of symbols are regular. That means if my alphabet, let's fix my alphabet A to contain, I don't know, 0, 1, A, C, and D. So my alphabet is 0, 1, A, C, and D. So I can create all strings from 0s, 1s, A, C's, and D's. What I'm saying that any finite set of symbols is regular. So for example, the language that contains 0, C, and D is regular. Why? So if I have letters in my alphabet and I take any of those letters, they together constitute a regular language. Of course, because it's written right here. So you can, this is a language generated by what regular expression? If I take 0, union C, union D. I know that each one of those letters is a regular set or a regular expression, so I take their union, constitutes something like this. So any alphabet you have, any finite subset will be a regular language. Okay? So now I'm claiming that natural numbers, this is an interesting one, is a regular language. So let me write you a set and you will see. So natural numbers with 0 is this set. 0, 1, 2, 3, 4, 5, and up to infinity. So it's an infinite set. And let me take an alphabet 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. This is my alphabet. So these are all the numbers I can use. And I'm claiming that natural numbers, all things, is a regular set. Can any of you, also in Georgian if you want, give me a description how to create natural numbers from these things? Huh? Άρα. So we can only take union, we can only take concatenation, and we can only take star. Okay, let's start. So you're saying 1, 2, 3, 4, 5, 6, 7, 8, 9. This set is regular, I agree. Then I do what? If I do star, so in this 10 is not in here, correct? 0 is also not in here. I want 0. So you're doing some. Okay, so. Logod? Do I take star here? You're on the right track, so I'll show you. Yeah, this is almost. So you take sets from 1 to 9, then you concatenate from 0 to 9, as you said, take a star, but it includes everything but just 0. So if you do this includes all natural numbers, but it doesn't include 0. Because what is this? So So this is all things like this. So this is 0, 0, 0, 1, 9, 2, 3, 4, 5, 4, 6, and so on. This the right side. The left side is everything, but that doesn't start with 0. All strings that do not start with 0. So 1, 2, 3, 4, 5. Not just do not start, that do not include 0. So these are all strings here that do not include 0. These are all strings with the 0. If you concatenate this thing, you will get all natural numbers but the 0. So for example, you will get things like 1, 0, 0, 0, 1, 9, which is 100,019. So if you concatenate this guy with this guy. But you need one more thing, namely 0, so you can take the union of this guy with 0, and that's it. Here it is in a way that yeah, that's correct. So this has to include this, otherwise you will not get 1. Yeah, I mean, but it's it's notational issue. If you do not, you can also add something like this here. But yeah, this star here includes the epsilon. Here, as it is written, the definition includes the epsilon. When we continue, we'll find out in there. So here we found out that this includes epsilon. Yeah, you can take it. Otherwise, you will not get 1. That is correct. Yeah. When you write plus, it does not include epsilon. When you write star, it includes epsilon. But I also said that when you're talking about the language, the definition that was given on that slide did not include epsilon, but somehow this one includes. But this is just a notational issue. Let's include epsilon. So somehow you get 1 from 9, this thing, and 0. So all natural. So you can only specify natural numbers, and this is as we said, regular language. Yet another regular language is variable names. So what does this describe? This describes something like, so you have letters from A to Z, and then again letters from A to Z, also including numbers and all possible strings. So for example, a thing like this is here, A9. So the fact that it is not written here, that means it's assumed. So it's just a notice. Sometimes they use it, sometimes they don't. So we might change it during the. But anyway, this is just a notational issue. Either you include it or you don't. If you do not include it, you just write it here. But anyway, so this is a variable name. So A9. I wrote 9. So in actuality, what you have here is not this, but rather something like this. Also something like A919Z. But basically all possible variable names are here, and I might write it this way. So instead we might write B17, meaning basically it's like B17, not even small b, but the big B17. So you can create all variables this way, but you cannot write really like small 17 here, but you take all letters and then concatenate with some word that includes letters and numbers. So let me give you what we are going to do next. Oh yeah, let's ask a question and finish with that. So let's ask a question here, and let's not enlarge it anymore. So now my question is the following. Let's say I gave you a regular language. That means I can specify it by constructing it from single letters, epsilon, and also unions, concatenations, and stars. if language is regular, does it mean that everything that is not in the language is also regular? Risi subset is ყოველთვის regularია. So here is the situation. Let me draw this. So you have your A star. So this is everything. And now you have your language L. Your languages are always like this. So let's say L1, there is an L2, there is an L3. So your languages are like subsets of everything. A star itself is regular because it includes everything, and you can define it each alphabet set, take a union, and then the star. Whatever. But what I'm saying is, let's say I know that L1 is regular. Does this mean that everything that is outside of L1 is also regular? It's not an obvious question to answer. So let's assume we know that this is true. Then we can answer the following question. If I have two regular languages, L1 and L2, then their intersection can be written this way. So let's look at, let's draw it here because my eraser stopped wrong. So let's say I have L1 and I have L2. Then their intersection can be written this way. Look at the complement of L1. This is everything that is outside of L1. This is L1 bar. Take complement of L2. This is everything that is outside of L2. Right? This here also. Take their union, which is everything here. So this is their union. I'm trying to color it. Union of the complements, and then the complement of the union of the complements is the intersection. So intersection of two sets is the same as if you take the complement of the first set, complement of the second set, take their union and take the complement. So let's say I know the complement of the regular set is regular. Then if L1 is regular, then the complement would be regular. L2 complement would be regular. Their union would be regular because union of the regulars is regular. And their complement again would be regular. And that would tell me that intersection of two things are regular. So if I prove that the complement of a regular set is regular, I know also that the intersection of two things is regular. And this is highly not trivial if you think about it. It means if I can exactly specify this guy by an expression in my computer, and I can specify this guy, that means I can also specify things that are here and here. But first, I have to prove that if I can specify something in my computer, I can also specify everything that is not in here. Somehow, intuitively, this is clear.